Hello friends, if you are taking strength of materials as your subject in mechanical engineering, this concept will be useful for determining bending moment and shear force in beams. Let's see what is shearing force. Shearing force is the algebraic sum of all the vertical forces to one side of the section in a beam, either to the left or the right side of the beam. And one more concept is bending moment. It is the algebraic sum of the moments about the section of all the forces, including the reaction acting on the beam, either to the left or the right of the section. To represent this in a form of graph, we have shear force diagram and bending moment diagram. Shear force diagram is a graphical representation of the variation of shear force along the length of the beam, whereas bending moment diagram is the graphical representation of the variation of bending moment along the length of the beam. In the next slide, we can see a sample of shear force and bending moment diagram of a simply supported beam with a concentrated load at the midspan. So I'll show you one example of a beam with shear force diagram and bending moment diagram. Hope it will help you in your studies. Thank you, and please subscribe to my channel.
Let's find the shear force diagram and bending moment diagram for the beam shown. Let's find the reaction forces at RA and RB. For that, let's consider moment at point A as 0, summation of moment at point A as 0 when moment is force into distance. Since 8 kilonewton and 6 kilonewton are pushing the beam downwards in a clockwise direction, it is considered positive force. So 8 into 4, moment is force into distance, so moment of A from the point C is 8 into 4 plus moment of A from point D is 6 into 6 distance, and since the RB force is pushing the beam upwards in the anti-clockwise, it's considered as minus RB into 10. So we get the value of RB. And next is the summation of all the vertical forces. Upward force is considered as positive, downward force is considered as negative. From this we get the reaction value at the point A. And for the momentum, just remember that the 8 kilonewton and 6 kilonewton are pushing the beam below like this. So momentum at A, 8 kilonewton is rotating the beam in the clockwise direction, so it is positive. Momentum at point A with respect to force D is making the beam rotate in clockwise direction, so it's positive. And when you consider with point B, the RB is pushing the beam in the counterclockwise direction. Just keep your pen at the point A and just consider the RB, and it's pushing in this direction. Calculation of shear force diagram. The upward force is considered positive, downward force is negative. Let's consider at Fa, which is equal to the reaction force Ra, that is positive 7.2 kilonewton. Between A and C there is no other load, so at Fc it is between A and C, which is considered as FC, that is 7.2 kilonewton minus 0. There is no force, so the 7.2 kilonewton remains constant. So at the point C there is 8 kilonewton, so since it's going downwards it's considered negative, so plus 7.2 minus 8 is equal to minus 0.8 kilonewton. And between C and D, which is FD, that is equal to minus 0.8, which remains constant. So minus 0.8 minus 0 is minus 0.8 kilonewton. At the point D, we have FD, that is, we'll carry the previous minus 0.8 kilonewton and subtract 6 kilonewton since it's going downwards. Then between D and B we have FB, which will remain constant since there is no load between D and B. So minus 6.8 kilonewton is constant. At FB we have reaction force RB acting, so minus 6.8 plus RB, since the RB is going upwards it's positive, so minus 6.8 plus 6.8 is 0. When you draw the shear force diagram, we got the RA value as positive, so consider this as 0 axis and this is positive x-axis and negative y-axis. So since we had got RA as plus 7.2, we'll mark a point at 7.2, and since the load, there is no other load in between C and A, it remains constant, so we mark here the next point 7.2. and since we got the force, vertical force at C as minus 0.8, we go down to 0.8, and then since there is no load between C and D, the 0.8 value remains constant. We draw a line as below, and at D we get minus 6.8, so we go down below till 6.8 and we mark 6.8 over here. And since there is no load between D and B, the 6.8 value remains constant, and since RB is 0, we close at 3. So this is the shear force diagram for the above problem. For bending moment diagram, remember this formula: M is equal to R into D minus L into D minus L into D. L is the load, R is the reaction force. So momentum at A is 0 since there is no moment at the point A, and moment at B is 0. To find the moment at C, just keep this point, so we know force, reaction force 7.2 kilo into 4 and minus 8 into 0. So MC can also be found out in the other way. Just keep a point at C, so R from here will be RB, so which is 6.8 kilonewton into the distances from here to here at 6, so 6.8 into 6 minus the 6 kilonewton into 2 minus 8 into 0. At C there is no distance, and at MD you have to find RB into 4 minus 6 into 0. RB is the reaction force, so this R is the reaction force, D is the distance. So you either start from left or right. Since we have found all the moments at respective point A, B, C, D, so at A it's 0, so So, and at C, moment at C is 28.8 kilonewton meter. So we mark a point and draw a line, and at D, moment is plus 27.2 kilonewton meter. So just below 28.8, little bit down, then you join like this on the point, and MB is 0, so this is the 0 point. Just from 27.2 draw to 0, so this is 0. So upward is positive, downward is negative. So this is the bending moment diagram.